Hello and welcome to our video solution to problem 13 for my spring 2020 final exam. In this problem, we are asked to compute the first and second order Taylor polynomials for the function 1 over x squared centered at c equals 1. So let's write down, just for reference, the formula for the kth Taylor polynomial. So t sub k of x. This is equal to the sum from 0 to k of, well, if we just have a generic function f, then we take the the nth derivative, evaluated at the center. All right. So in our case, the center is 1. So let me just write the 1 down. We divide by n factorial, and then we're going to multiply by x minus the center, which again is 1, to the nth power. Okay. And just in case you don't know the notation, where when we write down fn, this means the nth derivative of f. All right, so note that this is a sum. It is not just the individual term. So a very common mistake is that people will say, for instance, want to compute t2 of x. They'll just look at this term. They'll say, okay, take the second derivative, evaluate it at 1, divide by 2 factorial, multiply by x minus 1 squared, and then you're just done. But in fact, you want all the preceding terms as well, right? So t2 is going to, t2 of x is going to be t1 of x plus that n equals 2 term, right? So plus the second derivative at 1 over 2 factorial times x minus 1 squared. So computing t1 will be sort of a necessary step for computing t2. Now, the way I like to compute these things is by making a little table. So our n is going to be starting at 0, and it'll go to 1 and 2, and then we can stop there. Now, I'm going to have to know my derivatives. So let's see. Let's write down the derivatives just at x, just the function. So recall that if we talk about the 0th derivative, then we just mean the function itself. So this would be 1 over x squared. And I'm going to write this as x to the negative 2 because I generally like to take derivatives when things look like this. Okay, now I can take the first derivative and I'll get negative 2x to the negative 3, which I'll write in the other way. In fact, let me move this over just a tad. So we have negative 2x to the negative 3, which is also, right, negative 2 over x cubed. Why am I doing that? Well, I like to plug numbers in when it's in this left form. Okay, I'll take one more derivative, and that'll give me 6x to the negative 4, or 6 over x to the 4th. Okay, now we're not done with the table because we haven't computed fn of 1, just fn of x. So let's now compute fn of 1. Well, this is going to be pretty easy. All we have to do is evaluate these functions when x equals 1. So 1 over 1 squared is 1. Negative 2 over 1 cubed is negative 2. And 6 over 1 to the 4th is 6. Okay, so now I can write down, we'll start with t1 of x. So t1 of x, I'm going to be taking the sum from 0 to 1, which means there'll be 2 summands. So I'll need an n equals 0 term plus an n equals 1 term. When n is equal to 0, I get the 0th derivative at 1. Okay, that's a 1. Divided by 1 factorial. So I have 1 over 1 factorial. And then I'll have x minus 1 to the 0. Okay, we treat that as a 1. So in fact, this entire term will just be equal to 1. Okay, how about the n equals 1 term? Well, now I take the first derivative at 1, which is negative 2. I divide it by 1 factorial. Oop, this should have been the 0 factorial, excuse me, which is still 1, of course. I should have divided now this one by 1 factorial, and then I'll have x minus 1 to the 1. Okay, and now I can rewrite this as 1 plus, now this will be negative 2 times x minus 1. Cool. So that is my t1 of x, my first order Taylor polynomial. It's going to be 1 plus -2 times x minus 1. We don't want to distribute this. All right. We want to keep the center at 1. So we're going to write it in this form. Okay. How about t2 of x? Well, t2 we compute by just taking t1 and adding on the n equals 2 term. So this will be 1 plus -2 times x minus 1 plus, and now we need the n equals 2 term. All right, let's go back up and take a peek. When n equals 2, we need the second derivative at 1, which is 6, and we divide by 2 factorial. Okay, so we'll get 6 over 2 factorial, and then we multiply by x minus 1 quantity squared. And so we can now write this as 1 plus -2 x minus 1 plus, okay, 6 over 2 factorial is 3, so 3 times x minus 1 squared. All right, so we have found our second order Taylor polynomial for 1 over x squared centered at 1. And now let's see, there was a second part to the question, which we very often will overlook, but we should always go back, reread our question. And look what it says. Use these two Taylor polynomials, the first and second order, to approximate 1 over 0.99 squared. All right, let's see how we could do that. So, whoops, we're really jumping around here today. How about we'll use our T1 from right here. So T1 of 0.99, get our pen going, T1 of 0.99 is going to equal 1. And let's see, then we're going to have minus, those are minus, twice 0.99 minus 1. Okay, well, we know that 0.99 minus 1 is negative 0.01. If we multiply that by -2, we're going to get plus 0.02. So this will be 1 plus 0.02, which is 1.02. All right, so that's a pretty easy approximation for computing, right? Again, what are we computing? 1 over 0.99 quantity squared. All right, I wonder if we can do any better with the T2 approximation. So let's come down here. So T2 of 0.99. Well, we know that's going to be the T1 approximation plus an extra term, right? Because remember, this is our T1 of x. So this will be 1.02 plus 3 times 0.99 minus 1 quantity squared. Okay, well, again, 0.99 minus 1 is negative 0.01. But if we square this, it's going to end up being positive, and then, of course, everything's going to slide down another couple decimal places. We get 0.0001. Multiply it by 3, and we'll get a 3 on the end. And so this approximation for the value we want will be 1.02, and then plus another 0.03 on the end. All right, that's pretty good, right? We have an approximation out to 4 decimal places. Granted, that may be nothing like the actual value, but if we put it into a calculator, so the actual value, uh, 1 over 0.99 squared is, well, 1.0203, and then something really funny happens. You get 04, 05, 06, 07, and it actually keeps going like this for quite a while. It's kind of a funny number to play with, and you might even use these Taylor polynomials to try to figure out why it's going to happen this way. Okay, so that's how we can both compute some Taylor polynomials and use it to approximate the original function. Take care.